Hello everyone. Let's review the second set of topics covered in the rotational motion unit, which includes torque and angular momentum. Here we are looking at the rotational inertia demonstrator again. This time we will keep the moment of inertia constant and look at the force acting at a certain fixed radial distance from that rotation axis. A force acting at a distance from a rotation axis causes a torque. Torque is given the symbol tau and is calculated as r cross f, that's the radial vector crossed into the force vector. Tau can also be calculated I times alpha, that's the moment of inertia, times the angular acceleration. This is Newton's second law for rotation. Here we are going to cause a torque on the rotational inertia demonstrator. This will be an unbalanced torque. An unbalanced torque can cause a rotation and an angular acceleration. So let's let it go. We can see it's picking up speed, picking up speed, picking up speed. We also have a torque being applied in the opposite direction now. It's going to slow it down. Okay. I can take the mass off, so I do not have a force anymore, and I can cause a rotation again. This time the torques are balanced, so there is no angular acceleration. Now once we have a torque acting at this radial distance, that torque will have a direction associated with it. If we were just looking at the magnitude, counterclockwise torques are typically positive, clockwise torques are typically negative. However, torque does have a direction along the radial or the rotation axis. We can use the right-hand rule once again to do that. If I have this counterclockwise rotation and that torque is being applied in this downward direction to cause that, let's put this mass back on there. There we go. Wind it back up. Now, this force is going to cause a torque because it's acting at that radial distance, and we're going to get this accelerating in that direction. If I take my radial vector that's coming out in this direction, I take that radial vector and I cross into my force vector with my right hand. Here's the radial force. I will get a torque that's coming out of the page at this point. Okay, and that would cause this counterclockwise spin for you. If we've got that torque on the other side, I can wrap it around this way. Okay, the radial vector is in the outward direction. The force is in that downward direction. Okay, so I'm going to put my two vectors tail to tail. Alright, so I got the radius, and I got the force, cross them into one another, and I'll get a torque that's toward me, or into the page, or toward the back of the rotation axis. Let's take another look at the full Atwood machine, this time with a massive pulley. So the pulley has some inertia. We've got mass 1 hanging on the left, mass 2 on the right. Mass 1 is 10 kilograms, mass 2 is 5 kilograms. The moment of inertia of the pulley is 2 kilogram meters squared, and the radius of the pulley is 0.5 meters. There are three equations that we can set up with this problem. The main reason we need that is because Ft1, the tension in string 1, is different than Ft2, the tension in string 2. So the first equation we can set up is the unbalanced force on mass 1. That would be m1 times its acceleration, and that acceleration is going to be the tangential acceleration. So we've got m1 times at, and that's going to be equal to m1g minus ft1. Those are the two forces that are in a tug-of-war to accelerate that mass. The second equation we can look at is F unbalanced 2. That would be m2 times at. It's the same tangential acceleration as force 1. And then that's going to be ft2 minus m2g. So we've got that unbalanced force on 2 is equal to m2at, and that's equal to ft2 minus m2g. On the torque, we can take a look at the net torque that's acting on this object as well. The net torque is going to be I times alpha, but it's also going to be torque 1 minus torque 2. Torque 1 is the torque that's due to the first tension, Ft1, and then torque 2 is going to be due to the other tension, Ft2. We can also solve for alpha and AT, the angular acceleration and the tangential acceleration. If we take a look at that third equation that we just solved for, I times alpha is equal to tau 1 minus tau 2. If I substitute in R times F for the two torques, I can get I times alpha is equal to R1 Ft1 minus R2 Ft2. I can also then substitute in for alpha and Ft1 and Ft2. When I do that, I will get I times the quantity of AT over R. That's going to be equal to the radius R times that quantity M1G minus M1AT minus R times the quantity M2AT plus M2G. I can then move our R's over to the other side. Essentially, I divide both sides by R, and I'll get I over R squared times AT. That'll be equal to M1G minus M1AT minus M2AT minus M2G. At this point, we'll move all our AT terms to the left and all our G terms to the right. So I'll get I over R squared AT plus M1 AT plus M2 AT. That's going to be equal to M1G minus M2G. Solving for the tangential acceleration, AT will be equal to M1G minus M2G all over I over R squared plus M1 plus M2. And if I pull out that G, I will get AT is equal to the quantity M1 minus M2 times G all over I over R squared plus M1 plus M2. If you take a look at that equation, it looks very similar to our full Atwood machine equation that we had before without a massive pulley. The only difference is, in that denominator, we've got I over R squared. Well, that's like mass. Okay, that's the pulley's mass, essentially. So we've got that effective force divided by the total inertial mass in that expression. Well, if we plug in all our numbers, we'll get a tangential acceleration of 2.13 meters per second squared. I can also then solve for alpha. That'll be AT over R, and that'll give us 2.13 divided by 0.5, and we'll get a value of 4.26 radians per second squared for the angular acceleration, and that'll be in a counterclockwise rotation. Now we can solve for our two tensions, Ft1 and Ft2. To do that, we will go back to our linear force expressions. Ft1 is equal to M1G minus M1AT. I know all those quantities now, so I will just multiply M1 times that quantity G minus AT, and that'll give us 76.7 newtons. If I want to find Ft2, I will use that second expression, that second linear force expression that we had. Ft2 is equal to M2AT plus M2G. Again, I know all those quantities, so I'll substitute all those numbers in, and I'll get 59.65 newtons. Angular momentum is given the symbol L, and is calculated as R cross P, that's the radial vector crossed into the linear momentum vector, or R cross MV, that's the radial vector, cross that into mass times that velocity, that linear velocity vector, or tangential velocity vector. The magnitude of L can be found by multiplying R times P times the sine of theta, that's the cross product. And L can also be found by multiplying I times omega, the moment of inertia, times the angular velocity. Objects that are spinning have angular momentum. This mass is moving at a certain angular velocity. However, objects that are moving in a straight line can also have angular momentum relative to an observer off of that line of motion. Here we've got George is going to move along at a constant pace across the table. He has some mass. he has some velocity, and he's a certain distance away from you. Turns out that that radial distance r from you to George, if we multiply that by his mass times his velocity, that would be r times m times v. That's the same thing that we get right here. And if that angle between you initially is 90 degrees, we've got that Rmv sine theta, which is r times mass times velocity. Turns out that even when he's down along that straight line and that angle starts to change, we would still get r times m times v. So we can find his angular momentum compared to you. Conservation of angular momentum states that the angular momentum before an event is equal to the angular momentum after an event, or Li is equal to Lf. Some really neat things happen in nature because angular momentum is conserved. Spinning objects seem to behave strangely when they are trying to conserve angular momentum. Like me standing on this rotating platform on the floor and having a spinning wheel in my hand and trying to then change the direction of that spinning wheel. What I'm going to do is give this bicycle wheel a counterclockwise rotation. I'm going to hold on to it. Then I'm going to apply an internal torque. Okay, internal torque should not change the angular momentum that the bicycle wheel and me system had. But if I flip it around internally like this, now it's turning clockwise. So I have to turn counterclockwise. So let's see how that works. Okay, there it's turning counterclockwise. I'm going to apply an internal torque. And I start spinning around. And I can bring it all to a stop if I bring that back around in that direction. Now some other really neat things happen here. And we can see these types of motions on stabilizers for ships, out at sea, aircraft, even space probes like the Hubble Space Telescope. If I get this spinning, I can use gyroscopes like this wheel spinning right now to position objects like the Hubble Space Telescope in space. So there's no rockets on board that are going to change its direction. It's all done by gyroscopes just like this. Let's see one more demonstration of conservation of angular momentum. We can also change the moment of inertia to cause a change in angular velocity. If I hold on to these two weights at arm's length and spin, then bring these weights close to my body, I decrease my moment of inertia, and if there are no external torques acting on me, then I must increase my angular velocity to maintain the same angular momentum, just like this. Well, I hope the vodcast has helped you to review these processes. As always, feel free to ask any questions in class, and good luck on the test.